Hello everyone, my name is Fabrizio Montesi, and I am introducing this talk about multi-party languages, the choreographic and multi-tier cases. It's joint work with Saverio Giallorenzo, Marco Peressotti, David Richter, Guido Salvaneschi, and Pascal Weisenburger. Programming concurrent and distributed systems is notoriously challenging because the behavior that we want them to implement emerges from the interaction of multiple participants. To address this challenge, people develop new languages, whose distinctive feature is adopting a global point of view to define the intended behavior that participants should implement together. We call these languages multi-party languages. The development of multi-party languages has been a very active area of research, but also a very fragmented one. Different communities have simply developed different approaches. For example, multi-tier languages focus on making it simple to compose programs that should be executed by different participants. Instead, choreographic languages aim at expressing communication protocols such that the flow of interactions among participants is syntactically manifest. What we have found is that these two types of languages, which look different on the surface, actually share a deep technical link. Historically, choreographic and multi-tier languages have evolved separately for a long time. Examples of choreographies could already be seen in the late 70s for security protocols. The idea was then later picked up for things like specification languages, web services, and business processes. Scientifically, choreographies have been nurtured by the communities of process calculi and communicating automata. In a sense, multi-tier languages started from process calculi as well, because some key inspiration came from ambient calculi, but what actually gave birth to the research line was applying this inspiration to the lambda calculus. And then the ideas were picked up for programming the typical multi-tiered web applications consisting of a browser, a server, and a database, for example, and then later on even for general distributed systems. So the two approaches have been developed with different theoretical bases, process calculus and lambda calculus especially. They have different syntaxes, typing disciplines, and different kinds of results even. What this means is that we're talking about two communities that really have the potential to learn a lot from each other, and that's why we find the connection exciting. We could build a connection thanks to a coincidence, actually. Recently, both approaches have been applied to object-oriented programming in the Choral and Scalalogy languages. This was the first time that we had access to interpretations of the two paradigms within the same context, which allowed us to see clearly their differences and similarities.
Let's start with our running example. The sequence diagram on the slide represents a fragment of a single sign-on protocol where we find three participants or roles: a user, a single sign-on entity called SSO, and a server. The protocol starts with the user who sends its password to the SSO, and then assuming the password to be correct, the SSO authenticates the user and it sends to both the server and the user a token for later use. Of course, we can represent choreographies in text form. For instance, we can translate the diagram on the right using the syntax on the left. Actually, while performing our translation, we took the chance to extend the expressiveness of our protocol by interleaving interactions like user sends password PW to SSO at the first line with local instructions like the usage of the functionality check by the SSO to obtain the token at the second line. This is the essence of choreographic programming, which is a paradigm that uses choreographies as programming languages to define in a single artifact the interactions and the local computations expected to happen in a multi-party system. Choreographies resemble play scripts that describe the interactions among all the participants from an external point of view. We call this view objective. As a concrete example, on the right side of the slide, we find a possible translation of our protocol written in Choral, which is the first programming language that mixes choreographic programming and object orientation. The syntax of Choral programs is similar to that of Java. This is made on purpose to show that choreographic programming can be idiomatically integrated with other paradigms. Choral sneaks choreographies into Java-like code by extending Java types with roles using the et notation, which you can find marked in the snippet. For example, from the declaration of the class auth, we know it is shared between the three roles identified by the parameters user, server, and SSO. Choral classes can contain fields too. Here we have the two distributed objects called CH1 and CH2, which represent symmetric communication channels shared between the user and the SSO and the server. Then we see how Choral methods encapsulate choreographic protocols. Specifically, the method authenticate contains the implementation of our protocol. From the signature of the method, we see that it accepts a string that is located at the user, and it returns back to the user a token. In the body of the method, we found that local and distributed code integrate seamlessly. At the first line, we find the user who sends his password stored in the local variable PW to the SSO. This is done by using the COM method of the channel ch1, which transfers the string PW from the user to the SSO. At reception, the SSO uses the method check to locally generate the token. Finally, the roles perform two communications. One uses ch2 to send the token from the SSO to the server, which processes it with the method store. The second uses ch1 to send the token from the SSO back to the user as the return value of the method.
Multi-tier programming takes a different view compared to choreographies in the sense that we write the parts of our program that are located on a specific component from the perspective of this component. So on the left, you can see the interaction between the three locations, user, SSO, and server. In multi-tier programming, we represent going from one location to another by nesting lexical scopes. So the interaction protocol starts on the user, who sends the password to the SSO components and waits for an answer. The SSO component then checks the password, which means that the call to check is performed in the SSO context. After the check, the SSO component sends a session token to the server and the server stores the token. This is why the call to store is performed in a server context. As a last step, the SSO component returns the session token to the user, so the user receives the token as well. So in multi-tier programming, the language provides means to go from one location to another to execute some code on a different component. Because that code is then written from a specific component's perspective, we call this view in global programs subjective. On the right side, you can see our example implemented in the Scala-Loki multi-tier language. We use scoping to represent different locations. So in the example, you can see the scopes that are introduced by the on language construct. So the first line introduces a scope placed on the user, and the second line introduces a scope placed on SSO. The code in this lexical context then runs on the SSO component, for example, the password check on the third line. The fourth line then stores the token on the server location. So we now complete the authentication example by encapsulating the interaction protocol between the different locations in a multi-tier object. The multi-tier language might predefine a fixed distributed software architecture like a server client or a three-tier client-server database model. In Scala-Loki, however, you can specify the architecture yourself. So the language allows you to define so-called peers, which represent different locations of the distributed systems, and ties between peers, which specify the relations between components. Using this type-level specification, the compiler can statically ensure that remote access adheres to the defined architecture. For example, in the first definition, we specify that a user connects to a single SSO instance and a single server instance. And in a similar way, in the next definitions, we specify the one-to-one relations from the perspectives of the SSO and the server components. So the complete definition of the multi-tier object abstracts over the distributed components, their architectural relation, and their interaction patterns.
Having seen both programming models, now we take a look under the hood. How can we get executable code from them? From a single choreographic multi-party program, one local program is generated for each party. In this case, one local program for the user role, one local program for the SSO role, and one local program for the server role. This translation is called endpoint projection and performed by the choreography compiler. Similarly, from a single multi-tier multi-party program, one local program is generated per party by the multi-tier compiler. One for the user peer, one for the SSO peer, and one for the server peer. These local programs can then be run in parallel and will exchange messages to perform the protocols specified by the original multi-party program. Thus, we can see that multi-party programs can be described from an objective viewpoint with choreographies and from multiple nested subjective viewpoints with multi-tier, yet both map to the same execution model. In the paper, we substantiate this claim by giving a definition of minimal untyped variants of Choral and Loki and a translation algorithm between those. For this talk, let us only allude to the translation rules by contrasting how communication is represented in both models. On the left, in the first line, the user role sends the password to the SSO role, and in the last line, the SSO role sends the token to the user role. We can see, objectively described, we use one operation to represent communication over a channel by specifying source and target. On the right, In the first line, we enter the SSO viewpoint from the user viewpoint, capturing the user's password and taking it with us into the SSO scope. In the last line, we leave the SSO viewpoint and return to the user viewpoint, returning the token from the SSO scope to the user scope. We can see subjectively described. Every context switch between peers can represent two messages, one at the beginning and one at the end, while we specify only one endpoint in the syntax. The other endpoint is implicitly given by enclosing scope. The key finding of this work is that despite different programming models, both approaches follow a similar execution model.
This observation extends beyond the simple translation between choreographic and multi-tier programs. It points to a unified perspective and offers a bridge for comparing and transferring features between the two paradigms. In the paper, we explore this connection by focusing on four main features that are present in either language: higher-order composition of distributed programs, safe communication races, distributed data structures, and type-level topologies. Higher-order composition of distributed programs is a first-class concept in Choral. This is because in Choral, distributed programs and their state are objects in the sense of object-oriented programming. It is possible to create, store, and pass them around, as well as invoke their methods. Scala-Loci lacks an equivalent feature. At the moment, it supports only statically composed modules. This is not a limitation of the language itself, but an open challenge in the theory of multi-tier programming. Our perspective suggests that this requires a way to reconcile the subjective viewpoint of multi-tier code with the global nature of distributed programs. Safe communication races can be easily written in Scala-Loci thanks to the use of futures as a model for communication. Programmers can write multiple concurrent communication and wait for the first future that completes. Although races can be implemented in Choral, its type system has no way to specify them. This means that the compiler cannot check if the implementation of a race is actually safe. Our unified perspective suggests that adding existential role quantification to Choral would allow us to specify races at the type level. Distributed data structures can be easily written in Choral as a single cohesive entity without the need of a centralized orchestrator. This is thanks to the global viewpoint, which allows the type system to track distribution and ensure that the correlation between distributed components of a data structure is preserved through the execution of a choreography. Scala-Loci lacks an equivalent feature and only supports local data structures. Similar to higher order, the main challenge remains how to reconcile the global and local viewpoints in multi-tier programs. Dynamic topologies can be specified in Scala-Loci at the level of types and are enforced by the type checker. The language is expressive enough to capture many classes of topologies and their evolution as peers join and leave the system. In Choral, it's not possible to specify arbitrary dynamic topologies. This is because the type system requires that roles in a choreography are fixed during its execution. Although there are theories for choreographies that support peers and dynamic topologies, it was not clear how this could be applied to a full-fledged programming language like Choral. Our perspective suggests that adding universal and existential role quantification to Choral would allow us to specify dynamic topologies at the level of types as well. In general, our unified perspective provided us with a common ground for comparing the two languages and suggests a possible direction for transferring their features.
Let's take a step back. We have seen that both research areas have had a fruitful past and they have evolved almost in parallel for really long. In our paper, we have taken a step to compare and transfer knowledge between these two areas based on two concrete languages, Choral and Scala-Loci. Both of these languages are embedded in the object-oriented context. You can find more on this in the paper. For example, you can find the definition of the mini Choral language. You can find the definition of the mini Loci language, a description of the similarities leading to the translation algorithm, and the description of the remaining differences between these languages with an outlook on how to overcome those by transferring features from one language to the other. So the take-home lesson of this paper is that choreographies are described from an objective viewpoint, and multi-tier languages are a way to describe programs from a multiple subjective viewpoint, but they both map to the same execution model. So we hope that with this paper, we encourage researchers from these two communities to work together. And with that, we would like to thank you for your attention.